Good morning in Fukuoka, Japan. I will say it also in Japanese. Ohayo gozaimasu. Plastics started really being used in large volumes since 1945. In 1945, there were just 1 million tons of plastics produced. In 2021, we have had 400 million tons. Together with the growth in the plastics industry, many problems came along, such as pollution. And there is a lot of talk in the mass media and the general public about microplastics in the oceans. Microplastics in the oceans, in rivers, in lakes, but also microplastics in bottled water. And this is what I'm going to talk about today. What particle sizes are we talking about? Usually, microplastics are between 1 micron and 1 millimeter. Sometimes some researchers define microplastics up to about 5 millimeters. If it is less than 1 micron, then we talk about nanoplastics. It is perhaps the work of Sherry Mason, a professor from the State University of New York at Fredonia, that really attracted a lot of mass media attention. She examined 259 bottles, I think, of bottled water from different parts of the world. And as you can see in this list that was produced by Forbes magazine, by an artist, we have all the major brands in there, like Pepsi-Cola, Coca-Cola, Danone, Nestle. Of course, I have as a matter of fact, I have a bottle of Evian water that I'm going to drink during this presentation of mine. And what you can see here is that the average bottle of water per liter had 325 microplastic particles. And some of them, they had up to 10,000 microplastic particles, which is, of course, very disturbing. And these particles, by the way, they're not of all sizes. They were of sizes that could be detected by the equipment available at the laboratory of Professor Mason. And they go in sizes between 6.5 and 100 microns. So this work was featured in quite a number of TV programs, newspapers, and so forth. And after that, many other researchers started working on the subject. Sure, there was work before that, you know. I would say detection of microplastics in drinking water, tap water, as a matter of fact, goes back to perhaps in the 70s. Somebody detected microplastics, but it was not much of a problem then. It was perhaps not terribly well known to the general public. But recently, there's a lot of interest, and it's a problem that we have to address. Every year, according to this review paper, the average adult intake of microplastics is about 500,000 from tap water. And it's about 3.5 million from bottled water, 7 times more from bottled water than tap water. And as a matter of fact, I'm drinking at this very moment a bit of bottled water. What sort of methods of detection and identification of these microplastics do we have? The most common is perhaps micro FTIR spectroscopy, which is very well distributed. Another one, a bit more sensitive for smaller sizes, I believe, it's micro-Raman spectroscopy. And there are several issues relating to detection, related to identification, about sampling. You have to avoid sample contaminations because there is also plastic dust everywhere. In this very room from where I'm giving this presentation, there's plastic dust in the atmosphere. It would be plastic dust in the laboratory, so that sample contamination is one of the problems. There are questions about the limit of detection, depending on the equipment available, the method that a group of researchers is using. There's going to be different limits of detection. And there is a very good paper by a group of researchers from Europe, which is a critical review of the laboratory protocols, as well as a consensus of 12 European laboratories. And I would urge anybody interested in detection of plastics to take a look at this particular presentation. Now, the question is, how dangerous are microplastics to human health? A report was published by WHO in 2019, and they state, as you can read, that based on the limited information available of microplastics in drinking water, they don't really have any evidence of health risk. It does not mean there is absence of health risk. There is not evidence thus far that microplastics are not dangerous to human health. It is generally believed that those microplastics over 150 micrometers are not likely to be absorbed. And however, there is limited information for smaller sizes and for nanoparticles, so that more research has to be done. WHO was supposed to come up with a second report this year, 2022, and hopefully it will be coming out, and perhaps more information about this issue will be available. Now, the general public is sensitized to issues relating to the existence of microplastics in tap water, in the oceans, and of course in bottled water. While I was preparing the slides of this presentation last week, a friend of mine sent me a video. And according to this video, they said that they tested 22 volunteers, and 17 of them, they gave positive indication, identification of microplastics in their blood. And after that, I did search YouTube for other videos on microplastics, and I found lots of them. In the business world, they say that perception is reality. So that our business of polymer processing, must address this issue. It is very important. It is becoming better known to the general public, and we really have to address this question. Now, of course, the bottled water business is associated with the PET bottle. The rapid growth of the PET bottle industry started in the late 70s, I would say, and perhaps in the early 80s. Ironically, it is because of glass bottles. And in fact, Coca-Cola was producing the beverage in 1.5 liter bottles, which when you drop them, when you tip them, would explode. And in this particular picture, you see a professor from a nearby University of Toronto has set up a protective acrylic glass window in front of him, and he's handling a bottle of Coca-Cola, and by tipping it, this bottle would explode. You don't have to drop it, just by tipping it. And of course, in this particular case, according to a video that was presented at a Canadian news network, the bottle exploded and the glass shards went into the wooden panel that you see. Of course, it's a very dangerous situation. Quite a number of people were injured because of explosions. And I would say, I would perhaps have a pun that the explosions of the glass bottles resulted in the explosive growth of the PET bottle industry. How big is the industry? Well, it is huge. In 2021, 584 billion PET bottles were produced. And the numbers are growing. Of course, if too many people think that microplastics are dangerous, if they think that there are too many microplastic particles in bottled water, the growth of this industry will be curtailed. Let's take a look at a typical bottle, like the one that I have in front of me. And I have another one, a different brand, a different color. But the basic, of course, design is the same. We have a PET bottle, and the cap is normally made of HDPE. It is excellent for recycling, this particular product, because the PET is heavier than water, specific gravity 1.38. HDPE has specific gravity roughly of 0.95. And it is easy to separate PET from HDPE. So you can have a very nice stream of recycled material, PET and HDPE. But recently, we have also seen the production of caps made out of polypropylene. And polypropylene also has a specific gravity less than 1, and it is difficult to separate the HDPE caps from the polypropylene caps with this simple sort of experiment of just floating in water. The two of them, HDPE and polypropylene, cannot be repurposed together, so that if you have such a mixture, you are likely to be selling a recycled HDPE product at a lesser price. And as a matter of fact, I know at least of one company that went out of business because they could not sell HDPE, recycled 100% HDPE, because it was mixed with a bit of polypropylene. Typically, HDP would have a melt index between 1 and 2. PET around 0.8 is the intrinsic viscosity. So that these are very common materials used widely. And of course, that led to the growth in general of the plastics industry. What problems do we have in injection molding of the cap, injection molding of the preform for the bottle? Let's take a look at the typical mold. When two parts of the mold come together, right? At the point where they meet, there is going to be a bit of flash. So for another product that is not relating to bottles, not relating to caps for water, a small amount of flash would not really be a problem at all. It would not even be a nuisance. But in this case, is a big problem because even small, very, very small amount of flash in the cap or in the bottle is going to end up in the drinking water that a person is drinking from the bottle, right? So that even when you drink the water from the bottle itself, there might be a bit of microplastics stuck somewhere. And me, that I'm drinking it right now, I might be drinking a certain amount of microplastics. Now, in addition to the flash, we also have cavity gate marks. And you can see right here, the gate. And right here, there's going to be a cavity gate mark. And certainly, in these bottles I have in front of me, I can feel it with my hand, and I can see it very well. It is what is left over from the cavity gate mark. Now, this part of the bottle can easily be removed, can easily break up, right, into smaller pieces that can create microplastics, all right? Another problem that we may have in injection molding is that there's going to be a certain amount of surface porosity, which will lead to microplastic shedding. So that with flash, with gate marks, with porosity, we can easily have release of microplastics in bottles of water. Let's take a look at the preform. You can see here is the cavity gate mark. It's visible in this picture. And of course, it's right there at the bottom of the bottle later on. Now, the preform will eventually go to a blow molding piece of equipment to end up with this particular or a different kind of a bottle. Now, the preforms are made simultaneously in very few seconds in very large quantities. And I'm talking here about 96 preforms. Why I'm saying 96? Because I worked on a 96 cavity mold some 25 or 30 years ago. Now, you can take a look at it, and that's the kind of mold that we're talking about. This particular mold has 96 cavities. Right now, they produce molds with more cavities. I've seen one with 144, and I believe one with 156. perhaps they make more. So simultaneously, we may have 156 bottles. When the small parts open, they will drop down randomly. Each one of them has a cavity gate mark, which is something loose stuck at the bottom of the preform, which can easily break up and generate a lot of microplastics, can generate dust, will end up inside or outside the bottle. And of course, eventually we'll move on to the blow molding plant, and it's going to end up in the water that we drink. So we are going to have some microplastics, which are PET, polyester. Now, let's take a look at the cap. Now, I think this blue one is from this brand of water that I'm drinking right now, and this is from the outside. The gate, apparently, as I can feel it, it's really from the outside, the gate, the cavity gate mark. In the other cap, the cavity gate mark is from the inside. But you can see this particular cap has a lot of porosity. This one appears to have less, but there's a lot of porosity there. But my camera wasn't a camera. It was just a regular camera that I've been taking pictures during my visits in Japan and other places of the world, so that there is a lot of porosity in addition to the cavity gate mark, right? So porosity is another source of microplastics, release of microplastics, right? Let's take a look at the neck. You see this neck right here, you can see there is a thread. The thread has a different design in this particular bottle from this one right here. But you can see the top, there is a ring down here, but this part down is not something that you can thread the cap on. You can twist it on, right? So you have to thread the cap a little bit and then push it down. You won't do it by hand, of course, the machine will do it. But of course, during this time, you have a cap with porosity. You may have inside a cavity gate mark. There is pressure, there is stress that is imposed on the neck. Microplastics are likely to be released, and they will go into the water that the consumer will eventually drink. Well, what do they find? According to this group of researchers, I think they're from Munich, Germany. I will just have it written there the way they quoted it from their paper, that PET was 84% of the particles were PET, and 7% of the particles were polypropylene. And they state, as you can read, that this is not surprising since the bottles are made of PET and the caps are made of polypropylene. Now, polypropylene is not the most common cap material. It is not. It is HDPE. The question is, how come we have in this bottle of water 7% polypropylene and only 5% polyethylene? Well, this work was done in Germany. I do not really know the details, if they had bottles of water from Germany or other places, but I doubt it very much that there is more polypropylene caps in Germany than they are in North America. I think it would probably be less than 10%. That's my guess of caps of bottled water that would be made out of polypropylene, and most of them would probably be polyethylene, HDPE. Now, also, Professor Mason found in her research that for particles over 100 microns, 54% of the microplastics were polypropylene. Only 6% were PET. PEST is for polyester right here. 10% polyethylene. There is also polystyrene, and there is also nylon. Where do they come from? There's no nylon in bottled water, not in the bottles, not in the caps. Where did it come from? Contamination from the atmosphere, perhaps, from the, could be the injection molding plant, where they made the preforms, where they made the caps, perhaps from the potting plant. It could be from the laboratory, because there's a lot of nylon, there's a lot of polypropylene used in a lot of packaging, nylon used in a lot of products, clothing, right? Rugs that we have and so forth. And there is a lot of microplastics in the atmosphere. And those probably have contaminated polypropylene, nylon, polystyrene. They have contaminated the samples of water that were tested. So this is, so I put here this question about why so much polypropylene? I don't really know. Laboratory environment, as I said, it could be because polypropylene is brittle below 0 degrees. We don't know, but this is something that has to be examined, because the people that reported this kinds of results about the number of microplastics in bottled water were analytical chemists primarily, so that they did not worry about what kind of material was the cap made of, although they could easily see it because it's identified in all caps. There is the recycling numbers inside, could be 1 for PET, 2 for HDPE, and I would imagine that most of the caps tested were probably number 2, meaning HDPE. But they found more polypropylene. How come? It's a good question. Another group of researchers, also from Germany, they tested glass bottles. And when people hear about microplastics in bottled water, they think, well, we abandon PET bottles, we abandon plastic bottles. We're going to go to glass bottles. But look at this. 317 microplastics per liter was detected in glass bottles. Where did it come from? Well, the glass bottles were capped with aluminum, but aluminum by itself provides no sealing. The sealing material was HDPE. And in fact, they say that 81% of the microplastics resembled the PET-based cap sealing material. And they identified abrasion during opening and closing as the main cause of the release of these microplastics. a different group of researchers. This group of researchers is from Milan, Italy. They have tested single-use PET bottles. The methods used is SEM and EDS, energy dispersive X-ray spectroscopy, and apparently they claim that the detection limit is 3 microns in size. The total number detected, or I would say the average, was 148. The standard deviation is also shown there, which is also a lot of microplastics per liter of bottle. Perhaps they detected smaller sizes than the previous authors, right? Because they had a very sensitive detection method with a rather low detection limit. And they found that the PET bottlenecks and HDP caps were presenting the most serious source of microplastics, especially after opening and closing many times. On the other hand, the bottle itself, the polyester PET bottle, it was resistant to squeezing and crushing. Apparently, they did some testing. I don't really know the details of squeezing and crushing, but certainly they're available in their paper. It was, according to their method of testing, the squeezing and crushing did not really result in an increase of PET microplastics in the water. One thing that is very interesting is this one right here, that one brand of bottled water had about 64,000 microplastics on the inner cap surface after opening and closing 100 times. Now, brand 2 had 1.2 million microplastics on the inner cap surface were detected. Now, the third brand, as you can see, 334,000 roughly. And one third of them were less than 1 micron. So we've got a problem. How come brand 1 had only, I should not say only, but had only 64,000 as compared to 1.2 million? What was the difference in the HDP material? What was the melt index? What was the molecular weight distribution? What were the injection molding conditions? The flash that I was talking about, the perhaps the cavity gate marks, if they were absent or present, or the pressures that they were using during injection molding, whether the same or equivalent, similar, but certainly there were differences in the material and processing conditions of the caps of brand 1, brand 2, and brand 3. Now, to make things even more interesting is the fact that the small particles are the most dangerous, right? So the opening and closing does result in release of microplastics, and as a matter of fact, release of microplastics that potentially are more dangerous to human health, which means that if we want to improve this product, we must really study carefully the most suitable material for the caps and also the most suitable injection molding conditions that would result in release of fewer microplastics during opening and closing. There's another problem: plastic dust. In every plant that I've been at, extrusion or injection molding, there is a lot of plastic dust in the atmosphere. And this plastic dust in the atmosphere is a potential fire and explosion hazard. Perhaps we should add that it's also a hazard for release of microplastics into products associated with bottled water. Because in an injection plant, there's going to be an awful lot of plastic dust in the atmosphere. It's going to get stuck on the caps, inside, outside, whatever. It's going to get stuck on the preforms, eventually on the bottles. It's going to get inside the water. We're going to have a problem. And this is going to be later on detected. And so that plastic dust is another source of microplastics that we find in bottled water. What about slip agents? Now, in order for me to be able to open this bottle of water and have the first time I do it, in order to have a nice, clean, and easy removal, the cap, the HDP of the cap should have a low friction coefficient. However, by itself, HDP has a high friction coefficient. If this cap does not have any slip agent, it will be difficult for me to open. Perhaps I'm strong and I can remove this, but it will not be a nice, clean sort of removal of the cap from the neck of the bottle. So that slip agents are added, typically erucamide and behenamide. Now, the caps also must be stored because the erucamide or behenamide are added to the product, to HDP, before injection molding. So it needs some time for the slip agents to go through, to migrate to the surface, because on the surface is where they are needed. They're not needed inside, right? So that we want for this material to migrate to the surface, and because of their crystal structure, they have some plates, and these plates, they result into the slip, which is very easy, and then we can have a clean removal of the cap from the bottle. So that also, if we take a look at the design of the cap, let's take a look how this cap was injection molded. Injection molding, in this particular one, I think I have one bottle like this. I think it comes from possibly from a bottle of water that I purchased not too long ago. And the cavity gate is from the inside, so that from the inside, the polymer is entering, and then it has to travel through these tiny bridges to fill the lower ring. I examined a few years ago one such cap because it was a problem in an injection molding plant. They had difficulty filling the bottom ring in this particular case. And after a number of studies, the company that hired me, they managed to adjust the level of slip agent so that the slip agent would facilitate the flow of the polymer through these tiny bridges and fill. There were 8 bridges in that particular case. And I had calculated that the shear rate was about 100,000 reciprocal seconds. And of course, at such a high shear rate, there is definitely some slip occurring, but also the presence of the slip agent facilitates slip growth. And in fact, we verified it in our laboratory at McMaster University. And so that the slip agent is doing 2 jobs. One is filling of the bottom ring during injection molding. And secondly, it is used for easy removal of the cap by the consumer. So this is something that we have to think about, because we are likely to have, in addition to the microplastics problem by itself, we have also another problem with rucamide or behenamide, rich microplastics. And I do not know whether these slip agents are toxic. Probably they are not, because they are used in this kind of bottles, but together with large amount of microplastics, they might pose a problem if they remain in the human body for a long time. This is another issue that has to be examined. And with that, I'd like to show you these slides that historically the humankind has named the great ages according to the material that they use. And that's why we have the Stone Age up to 3200 BC. We have the Bronze Age. We have the Iron Age from about 1800 to present time. We have a lot of steel and aluminum. And from 1922, we have the Polymer Age. And we at the Polymer Processing Society were the frontline custodians of the Polymer Age, right? Because we do research for these products. The chemists, they produce the polymer, but we produce the final product that is reaching the consumer, so that we really have to deal with this problem, the problem of microplastics in ocean waters, the problem of microplastics in tap water, and the problem of microplastics in bottled water. And I'd like to thank you for your attention. And I will say it also in Japanese. Domo arigatou gozaimasu.